Good evening everyone. My name is Deblina Maiti. I am a research scholar in the Department of Mathematics, IIT Kharagpur, and I am also an NPTEL TA for this course Real Analysis 2. And this is the fourth problem solving session. And in this session, we will discuss about Stone-Weierstrass theorem and differentiation in several variables. So we'll start in a few minutes. Okay. So in R or C, the complex plane, every bounded sequence of complex number has a convergent subsequence, right? Has a convergent subsequence. Right? Now the question is this theorem true in the sequence of functions? So now question is, this true for sequence of functions? Right? Now in sequence of functions there are two types of boundedness, right? One is pointwise convergent and the other one is pointwise bounded and the other one is uniform bounded. So pointwise bounded and uniform bounded, right? So what is pointwise bounded? A sequence of function is pointwise bounded if mod fnx less than some phi x for each x belongs to this set E. So first suppose fn is a sequence of function defined on E, right? Now pointwise bounded means for each x it is bounded by some phi x. At each point it is bounded by phi x, and for all n equals to 1 to infinity, right? And for uniform boundedness it means all the fnx is bounded by some number for all x belongs to E and for all n equals to 1 to infinity, right? So this is the difference between pointwise boundedness and uniform bounded, right? Now we'll show that uniform boundedness of fn will not guarantee the existence of a convergent subsequence, right? So we'll give an example. which shows that uniform boundedness of Fn does not imply existence of a subsequence of Fn which is pointwise convergent. So here boundedness does not imply existence of a convergent subsequence, right? So the example is, so take Fnx to be sin nx. Okay. Where 0 less equals to x less equals to 2 pi, n equals to 1 to infinity, right? Now it is a uniformly bounded sequence because each Fnx is bounded by 1, right? So Fn is uniformly bounded, right? Now we'll show that now suppose there exists a subsequence which is pointwise convergent. So suppose there exists a sequence nk such that this sequence sin nkx, the subsequence sin nkx converges for every x belongs to 0 to 2 pi, right? Suppose there exists some sequence, so it is convergent, so it is also Cauchy, so then it will imply limit k goes to infinity sin nkx minus sin nk plus 1x equals to 0, right? Because it is Cauchy, so since it is 0, its square is also 0, goes to 0 as k tends to infinity. Now it will, since it is uniformly boundedness, and then it will follow from the dominated convergence theorem, which we will learn later, that 0 to integration 0 to 2 pi, that is integration of this quantity, will also be 0 as k goes to infinity, right? So this line comes from by dominated convergence theorem. We'll talk about it in some later classes. Okay. So by dominated convergence theorem, the integration will also go to 0. Right. Now, look at the integration of this term. We can integrate it term by term. So if we integrate it by taking its square, so it will be sine square So integration of this quantity, oh actually it is 0 to 1. So what we are doing here is that we are taking a sequence fn which is uniformly bounded, but there does not exist any subsequence of fn which converges pointwise, right? Because in R every bounded sequence has a convergent subsequence, but this is not true for sequence of functions. So we have taken this sequence sin nx and we see that fn is uniformly bounded, and the integration here we come 0 to 1 sin nkx minus this, and this integration will be, this will go to 0, this term since nk and nk plus 1 are different, and these two will give pi, so it will be 2 pi. So the value is 2 pi. Okay. So this is a contradiction because we have already got this is going to be 0, but we found out that the integration, each of this integration is 2 pi, so as k tends to be infinity it also goes to 2 pi. So this is a contradiction. So there does not exist such subsequence which converges for every x in 0 to 2 pi. So it is not convergent. Okay, so fn pointwise convergent subsequence. Okay. Now another question is, if it is the sequence is convergent, does it imply the subsequence is uniformly convergent? So next question is, does every convergent sequence contain a uniformly convergent subsequence? So here the answer is also no. So the counter example is, take fn x to be x square by x square plus 1 minus nx square, where 0 less equals to x less equals to 1. So each fn x is less equals to 1, it is uniformly bounded, right? Fn is uniformly bounded on 0 1, and when n goes to infinity fn x is also 0, right? When n goes to infinity, for every 0 less equals to x less equals to 1. This means what? This means fn goes to the 0 function pointwise. Fn converges to 0 pointwise. Now fn of 1 by n is 1. So supremum of fn x minus, that is 0x, the converges to 0 function. So in 0 1 is actually x belongs to 0 1 mod fn x, right? And the supremum value is 1 because it is taking the value 1 at 1 by n. So supremum is one which does not converge to 0. So this sequence is not uniformly convergent, because we know from real analysis that if fn converges to f uniformly, then the supremum of fnx minus fx goes to 0 as n tends to infinity, right? So this implies no subsequence of fn can converge uniformly on 0, 1. Right? Now we discuss the definition of equicontinuous. So a family, this script f of complex functions f defined on a subset E in a metric space xt is said to be equicontinuous on E if for a given epsilon there exists delta greater than 0 such that mod fx minus fy is less than epsilon whenever d of xy is less than delta for all x belongs to E, xy belongs to E, and f belongs to this script f. So for a given epsilon, this delta works for every function in the set script f, right? So for continuity we get, for given epsilon we get a delta for each function, but equicontinuity means we are getting a delta, only one delta for given epsilon for the whole class f, means for every, this delta will work for every function in this script f, right? So this class we have defined here, this fnx in this question, we will show that this is not equicontinuous. So this in example, this fnx we have defined by x square so we'll show that the family, this fn is not equicontinuous. So not equicontinuous means, so we choose a epsilon half, right? Now it is not equicontinuous means for each delta greater than 0 we will find some xy such that, so this not equicontinuous means for each delta greater than 0 there exists some x delta y delta such that d of x delta y delta less than delta implies mod of fx delta minus fy delta is greater or equals to epsilon, right? So you have to find this. So for each delta, so choose delta. Now for delta greater, for any delta greater than 0, we can find there exists some natural number such that 1 by n is less than delta, right? So this means mod of 1 by n minus 0 is less than delta. So we are choosing x delta to be 1 by n and y delta to be 0, right? So the difference d x delta y delta is less than delta, and mod of f fn x delta minus fn y delta is what? So fn x delta is 1, right? And fn y delta means fn 0 is 0. So it is actually 1, which is greater than our epsilon. So it is not uniformly. So fn is not equicontinuous, right? So there is a relation between equicontinuity and uniform convergence of sequence of continuous function, right? So there is a relation between this equicontinuity and uniform convergence of sequence of continuous function. Right. So there is a relation between them. So this following theorem will show the relation between these two things. So the first theorem is if K is compact, in a metric space, compact metric space, if Fn belongs to this Ck, which is the space of all continuous functions defined on K, right? So K is compact and Fn we are taking from Ck, that is Fn is continuous in K for n equals to 1 to infinity, right? And if Fn converges uniformly on K, then Fn will be equicontinuous. So in compact set, if Fn converges uniformly on K on compact set, then Fn will be equicontinuous, right? And each Fn should be continuous. Fn belongs to Ck, right? In this example, each Fn is continuous, but Fn converges to 0 not uniformly. Fn converges to 0 pointwise. That's why it is not equicontinuous, right? And for the other case, which is theorem 2, which says if K is compact, Fn belongs to this script K, means each Fn is continuous for n equals to 1 to infinity, and if Fn is pointwise bounded, and equicontinuous, on K, then Fn will be uniformly bounded and Fn has a uniformly convergent subsequence. So Fn contains a uniformly convergent subsequence. Right? So in theorem 1, so if Fn converges uniformly on K, then it will imply equicontinuity, and theorem 2 is see that if it is pointwise bounded and equicontinuous on compact set, then it will imply uniformly bounded and contains a uniformly convergent subsequence. Right? Now we'll state the Stoney-Stress theorem. This theorem comes from these two results, this theorem 1 and theorem 2. So this is the Stone which says if F is a continuous complex function on the closed interval AB, then there exists a sequence of polynomials Pn such that Pn converges to this F uniformly on this closed interval AB. Right? If it means every continuous function can be approximated by polynomials. Right? So this is the Stoney-Stress theorem, and now we'll move forward to the differentiation in several variables. Okay, so in R, F is differentiable means what? In R, F is a mapping from R to R is said to be differentiable if limit h goes to 0, f of differentiable at a point, say differentiable at a, suppose if limit h tends to 0, a plus h minus fa by h, this limit exists, then we'll say that this is f is differentiable, right? And then we denote it by f dash a, right? And then we denote it by f dash a, right? So in other terms, we can write this as f of a plus h minus fa equals to f dash a h plus some rh, where limit h goes to 0, rh by h goes to 0, equal to 0, right? Right? So what we have done here is that we have written f a plus h minus fa as a sum of a linear functional f dash a h plus some small remainder, right? So we have written f of a plus h minus f a as a sum of f dash a h. We are writing f dash a h as a linear functional, the sum of a linear functional a such that h goes to f dash h, right? This is the mapping a plus some remainder, small remainder, right? So we are approximating this f a plus h minus f a with a linear functional, right? Now linear functional, so I hope you guys know a bit of linear algebra, right? So a mapping here, so I'll just write a mapping t from x to y is said to be a linear transformation if t of x plus y equals to tx plus ty and t of cx equals to c of tx, where this c is a scalar, right? So then it is a linear transformation from x to y. And here if y equals to x, then we call t as a linear operator. Both domain and codomain are same, so we call it, then we call t to be a linear operator. And if y equals to r or c, these two fields, then we call t a linear functional, right? And here Lxy denotes the set of all linear transformation from x to y, right? So just recall the definitions and linear operator, linear transformation and all that, basis, dimension, okay? A bit of linear algebra we need here. So we have written f a plus h minus f a as a linear functional, this, so here this a is a linear functional a from r to r, where this h goes to f dash a h. So a is a linear functional, right? So we have written f of this by linear functional a and a small remainder, right? So what we are writing is this, f of a plus h minus f a equals to h plus rh, right? So we regard derivative at x not as a real number but as a linear operator on R that takes h to f dash x, where ah is f dash x h, right? So we are approximating, we are writing the derivative as a linear operator. So now we'll give the definition of differentiation in several variable with respect to linear operator, linear transformation. So definition, so suppose if take E is a subset, E is an open subset of Rn, and if from E, which is a subset of Rn, to Rm, a mapping, right? Now let X belongs to E. Okay, so if there exists a linear transformation A from Rn to Rm such that limit h goes to 0 modulus of f of x plus h minus fx minus ah by mod h equals to 0, then we say that f is differentiable. At x, and we write this differentiation f dash x to be a, right? So here f dash is a linear transformation and a is a linear transformation, right? So f dash equals to a means the derivative of this f is a linear transformation. So we are writing derivative of f as a linear transformation, not a real number here. When f is from R to R, then it was a real number, but when f is a mapping from Rn to Rm, then the derivative will be a linear transformation, not some number. And we know that from linear algebra that every linear transformation from Rn to Rm can be uniquely determined by a matrix of order m by n, right? So we know that every means from linear algebra, recall that this L Rn Rm means the collection of all linear transformation from Rn to Rm, right? And this class, this m n by n, the class of all matrices of order m by n. So there is a 1-1 correspondence between these two. How? If we take a linear transformation, we will get a unique matrix with respect to some basis, maybe standard ordered basis, right? I'm writing this SOB means standard ordered basis, right? And if we take a matrix, we can also get a linear transformation using the basis, right? This will be TA. So this is elementary form linear algebra, right? So here our f dash is a linear transformation, the derivative. So we may write f dash in terms of matrices also, right? since f is a mapping from Rn to Rm, so this f dash is actually A, so A is a linear transformation from Rn to Rm, right? So f dash is A means f dash is actually can be represented as a matrix also, right? So here differentiation means approximation of f of x plus h minus fx, right? So we'll see some examples. Now first, so we are differentiating a function from Rn to Rm. So what if the function is linear? Function is a linear transformation. Then what is the differentiation of a linear transformation? So the first problem is, suppose f from Rn to Rm is a mapping and f belongs to L Rn Rm, means f is a linear transformation from Rn to Rm, right? Then what is f dash? The first question is f differentiable, and second is what is, if it is differentiable, then what is f dash? So we'll show that this f dash x is nothing but f here, okay? So here f is a linear transformation, so f dash equals to f means f dash is also a linear transformation, right? So we'll prove this. So this is easy actually. So f is a linear transformation, so f of x plus h, let x belongs to Rn, right? So f x plus h minus fx is f x plus fh minus fx, which is equals to fh, right? So it is differentiable means what? It is differentiable means there exists some A linear transformation from Rn to Rm for which this happens, this one, right? So we have already found here that f x plus h minus fx minus fh is actually 0. So modulus of this is also 0. So we can write this by mod h goes to 0. So here this means what? This means AH here is actually FH, right? So this A is actually F, means F dash, it is differentiable, and F dash x is nothing but F, right? So if F is linear, if the mapping is linear, then the derivative is itself, right? Okay, let's go to the next problem. So the first one is, if S from R2 to R is defined by Sxy equals to x plus y, then what is the derivative of this function? S dash xy is what? Right? And for the second one, if P from R2 to R is defined by Pxy equals to xy, then it will be differentiable, and we have to find p dash xy, right? Okay, so for the first one, A, it is clear that S is linear, right? Because S of xy plus some hk will be S of xy plus S of hk, right? So S is linear. So you have already seen in problem 2 that problem 1 that if f is linear, the derivative will be itself. So S dash is going to be S. So S dash of xy is actually S, right? Now for the second one, so p xy equals to x into y. So it is not linear, right? So it is not linear. So we have to find a linear transformation from R2 to RA such that this occurs, this line, right? So now we are going to take A to be this BA, where this point AB belongs to R2, right? So A is a linear transformation. So we can write linear transformation as a matrix, right? So A equals to AB means what? A equals to AB means A xy, the linear transformation is actually, sorry, not comma, this matrix BA into xy, which is bx plus ay, right? So A is a linear transformation, and linear transformation can also be represented by matrices. So we have taken A to be this matrix BA means this is a 1 by 2 matrix, right? So now matrix, this is A is 1 by 2 and xy is 2 by 1, here 1 by 2 order, and it is 2 by 1, so it is bx plus ay, right? Ax equals to this. Now we have to find the limit hk, here the point is this ordered pair, so mod of p ab plus hk minus p ab minus a hk by mod of this hk. We have to show that this goes to 0. So this is hk goes to 0 plus of p a plus h b plus k. ahk is right, and modulus of hk is h square plus k square in R. So limit, so this will be and this is going to be mod hk by root over h square plus k square, right? Now we'll use this. So mod of hk is actually less equals to root over h square plus k square always, right? So using this, we'll see that this, so this is less equals to or less than limit so it is root over h square plus k square, and which is 0, right? So this value is going to be 0. Less than 0 means it is modulus, it is positive, so it is going to be 0, right? So this is 0 means p is differentiable and p dash x p dash ab is going to be a, right? So this implies this p dash ab is actually a, right? So p dash ab is a linear transformation, right? So if it operates in at the point xy, then it is going to be axy, which is bx plus ay, right? Okay, so p dash ab xy is nothing but bx ay. Okay, so p is differentiable and p dash is a. A means this matrix ba. So ba into xy will be bx plus ay, right? Okay, now we'll define partial derivatives. So now we'll go to partial derivatives. Okay, so now our f is a function from Rn to Rn, right? So f is a function from Rn to Rn. Now take this ei, this is a basis, standard ordered basis of Rn, where this ei is nothing but 1 in the ith term and then 0. There is n term, and uj is a basis of Rn, right? Where uj is 1 in the jth term and the other terms are 0. This is m tuple. Uj's are m tuples and ei's are n tuples, right? So now f is a mapping from Rn to Rn, so you can also write, so x goes to here, fx, right? So you can also write f by component, right? Like f1x, f2x and fmx, right? So we are writing f as f1, f2, fm, where these fi's are mappings from Rn to R, right? For I, where I varies from 1 to m, right? Now suppose a point A belongs to Rn. So A can be written as a1 a2 to an, right? Now the partial derivatives djfi of x, or a is, so we are differentiating I in the jth term. Okay, so it is going to be fi a1 a2 are all the things are fixed, only jth term is changed to aj plus h minus fy of a, right? A means a1 a2 to a by h, right? So only the jth term is changed to aj plus h, right? So it is actually fy of a plus h into ej minus fa by h, right? Because ej is what? Ej is 1 on the jth term and the other terms are 0. So fy of a plus h ej minus fa by h. So if this limit exists, then we say, so if the above limit exists, then this djfi is called the the jth partial derivative of fi, right? Now we have seen that this if f is a mapping from Rn to Rm and it is differentiable, then this f dash x is a linear transformation from Rn to Rm, right? F dash is a linear transformation, so f dash can be written in terms of matrices. So now by this theorem I am going to write, we can write f dash x in terms of matrices where the elements of these matrices are partial derivatives of these fi's. Okay, so f from Rn to Rm is differentiable at a point x belongs to Rn, then the partial derivative this djfi x exists. Fi's are the components of f, right? Exists, all the partial derivative exists, and f dash x ej is here, this ei's are the basis of Rn and ui's are the basis of Rm, right? Where 1 less equals to j less equals to n, and right. So if it is differentiable, then all the partial derivative exist, and f dash x ej equals to this. Now this in this theorem, what is f dash j actually means? This f dash j x ej, f dash is a linear transformation, right? So f dash is a matrix of okay, so f dash belongs to L Rn Rm, right? So the matrix of f dash, which is denoted by this f dash x, then belongs to m by n. It's a matrix of order m by n, right? Now f dash x ej is nothing but the matrix of f dash x into f dash x can be written by this matrix. This is of order m by n, and ej is what? Ej is this matrix 0 to 1 0 1 in the jth term, right? This is of order n by 1. So what is this mean? This means it is ej, so it is the jth term. So we are multiplying a matrix with this unit vector ej, which is 1 on the only on the jth term, right? So multiplying this will give the jth column vector of this f dash x, right? So this is actually the jth column vector of this matrix f dash x, right? So the jth column by this theorem actually gives tells us that the jth column will be of this form, right? And for all every j from 1 to n, we'll get every column, so we'll get the matrix f dash x. So f dash x will look like this one. So the matrix of f dash, so what we are saying is that the jth term will be like this, right? So suppose j is 1, so the first column will be sum of d1 fi x into ui, right? Ui is at the basis, so the first term will be d1 f1 of x, right? This is a column, so first term will be d1 f1 x, right? And then the second term will be, so here in this one j is fixed, so suppose j is 1, so I is varies from 1 to n, so fi's are varies from 1 to m. So the next row it will be fi's are varies only, so d1 f2 x, and then goes on like d1 of if I runs from 1 to m, so it will be dm x, right? So this is the first column, and the second will be like this. So here j is 2, so it will be d2 f1 x, d2 f2 x, and so on, d2 fn x. And the last column will be, last column means j is n, right? So it will be dn, j is n, so dn f1 x, dn f2 x, and so on, this will be dn fm x, right? So it is a matrix f dash x. So we are writing f dash in terms of the partial derivatives of f, right? So f dash is a linear transformation, means f dash is a mapping, can be represented as a mapping, and f dash can be represented by this matrix, this one. This is the form of f dash. Right? Okay. Now, if M is 1, so F is a matrix from mapping from Rn to Rm, right? If M is 1, means F is a mapping from Rn to R is differentiable, and then this grad fx defined by equals to this vector d1 fx d2 fx, this vector dn fx is called the gradient of f at the point x. So it is actually so f is Rn to R, right? So here this all these fi's f1 f2 fn are Rn to R. So each of this row is actually row vector. Each these row vectors are gradient of this f1 f2 and so on, right? So this d1 f d2 f, so this here also d1 f1 d2 f1 and dn f1, right? Now if what is this actually means, if h belongs to Rn, then h can be written as some hi ei, right? I equals to 1 to n, right? So f dash x is a linear transformation. Now it is operating on h, means f dash x sum of hi ei, since hi's are scalars, right? ei's are vectors, hi's are scalar, so it will be h1 f dash x e1 h2 f dash, since it is linear, so it is the scalar will be in front, so it is f dash x e2 and so on. This is hn f dash x en, right? Now f dash x e1 is what? F dash x e1 is the from here, since f is a mapping from Rn to R, so from theorem 1 will be, it will be only d1 f, right? So by theorem 1 it will be h1 d1 f x, and it will be d2 f x and so on. It will be hn dn f x. So it is gradient of f at the point x dot product h, right? Because gradient of f was this So f dash h, so what we are getting here is this, that f dash x h, a vector, is actually gradient fx dot h. This one we are getting, right? So we have written f dash in terms of gradient of f. Now we'll define directional derivative. Okay. So let f is a mapping from Rn to R, right? For x belongs to R. So here we have seen that in partial derivative we have defined here this dj fi is this one, fi of a plus h ei. H ei means it is ei is a unit vector, and h, so we are differentiating in the direction of ej, right? And since ej's are unit vectors, so these are the axes, so that's why it is a partial derivative with respect to the axis, right? Now I am we are going to derivative it in another direction, may not be the axes, in any other direction, right? Like in R2, in R there are only two direction, right? So that's why we take h plus, h goes to 0 plus, and h goes to 0 minus if it is 0, right? From the left or right there is only two direction. But in case of R2, if it is this point 0, then E1 is suppose the x-axis and E2 is the y-axis, right? This is the basis, the x-axis and y-axis. Now there are also infinitely many directions left, so we have already done differentiation, partial derivative in terms of x and y, in the direction of x and y, that is the partial derivatives. Now we are trying to derivative f in other direction, because we can reach 0 0 this point from many direction, right? There are infinitely many direction. If it is this direction b, now what is the derivative of f when we approach f from this direction, right? So that's why we are interested in directional derivative of f. We have already differentiated in the axes, in ei, ej, right? Now suppose f from Rn to R, and now if the limit h goes to 0, f of a plus h v minus fa by h exists, then it is denoted by dvfa, that is differentiation with respect to differentiation of f in the direction b, dvfa, and it is called the directional derivative is called the directional derivative of f at the point A in the direction v. Right? So we have already defined partial derivatives, and now we are giving the definition of directional derivative. Right? Now if we take the direction to be ei and ej, then now here note is that if means dei f a is actually the partial derivatives di f a, right? So if v is taken to be ei or ej, then it will give the partial derivatives. And also if is differentiable at a, then dx f a is actually the f dash a into this x, this vector. Right? Now we'll solve some problems from this differentiation. So the first one is prove that the function f from R2 to R defined by fxy and 0 otherwise. So it has a directional derivative at all direction. So has well defined dvf00 for every v, but f is not continuous, f is discontinuous. So here at the point 0, 0, all the directional derivative exist, but f is discontinuous at 0, 0. Right. So for the directional derivative, so here the point is 0, 0, right? So for directional derivative, we check this. So dv f00 is limit h goes to 0 f plus h of v, right? So this direction can be taken as some AB, right? So h AB minus f00 by h, right? This is the definition of dv f00, the derivative of f in the direction v, right? The direction of v is I have taken AB, right? So it will be f of f00 is 0, it will be h, and it is going to be ab square by right? So this gives the value b square by a if a not equals to 0, and if a equals to 0, then it is going to be 0, right? So this dv(f)(0)(0) always exists. If a is 0 or not 0, it always exists, right? So all the directional derivative exist. So this implies dv(f)(0)(0) exist for all direction v belongs to R2, right? AB is any number in R2, right? So in all direction, since AB is arbitrary, so the direction is arbitrary, so directional derivative exists in all directions. Now we'll show that f is not continuous, right? So continuity means what? Continuity means if we reach 0 0 from any direction, so this means continuity means if xy goes to 0 0, then f of xy will go to f(0) 0, right? This is the definition of continuity, right? So now xy belongs to R2, so we can reach 0 0 from any direction. Still, if f is continuous, then f xy will also go to 0 0, right? Now we approach 0 0, we can approach 0 0 from any direction, right? But if f is continuous, then f xy must approach to f(0) 0, which is actually 0, right? f(0) 0 is 0. Now take this direction, so choose x equals to y square, right? So x equals to y square means this y square y, this gives a direction, right? This is another direction, means maybe this curve, is y square y. This is actually x square y, x equals to y square, it is a parabola actually. Maybe this one. So we are approaching 0 0 from this curve, right? Now if f is continuous, then f of y square y must go to f(0) 0 as y goes to 0, right? If f is continuous. And we'll see that f y square y will not go to 0. So what is f y square y? So f y square y is the value y to the power 4 by right? So it is 1 by 1 plus y square. So when y goes to 0, f y square, so when y goes to 0, f y square y goes to 1. So it not equals to f(0) 0. So this means f is not continuous. So this implies f is not continuous at 0 0, right? So let's go to another problem. So suppose f is a mapping from R3 to R2, and it is given by this f of xyz equals to, so it is a point of R2. We can also write it in terms of components f1 f2, where f1 and f2 are mappings from R3 to R, right? So f1 of xyz is a real number, so it is x square plus z, and f2 of xyz is plus xz. Okay. Now prove that f is differentiable at any point, at every point of R3, and find the mapping f dash x, this matrix f dash x. F dash x is a linear transformation from R3 to R2, so it is also can be given by matrix, so you have to find this f dash x also. So first we have to prove f is differentiable, right? Now there is a theorem which says if all the partial derivative exist and continuous, then the function will be differentiable, right? Here all the points, components f1 f2 are f1 is polynomial, so all the partial derivatives of f1 is going to be continuous, and for f2 also all the partial derivatives will be continuous, so f is going to be differentiable, right? So this result I will write here. This is, recall this theorem that if f from Rn to Rm, then f dash x exists if all the partial derivatives dj fi x exist in an open set containing x, and if each djfi is continuous at x, right? So by this theorem, this f in problem 4 will be differentiable. So f is differentiable. Now you have to find the matrix of f dash. So you have already written here how this matrix looks like this. So f dash x will look like this, the matrix of f dash x: d1 f1, d2 f2. So each column will be d1 f1 d2 f2 like this, right? So here f dash x is what? The matrix of f dash x is, so it is a mapping from R2 to R3 to R2. So the matrix, the order of the matrix will be 2 by 3, right? So it is d1 f1 x, d2 f1 x and d3 f1 x, and next row will be d2 f1 d2 f, sorry, it is d1, and then d2 f2x and d3 f2x. So this is the matrix, right? Matrix of f dash. Now just you have to find the derivative, partial derivatives of f1 and f2, right? Then we will get this matrix actually. So it will be 2x minus 1 1, and this term will be sin z plus z sin z. This is a matrix of f dash, right? And the gradient of f1 f2 will be the rows of this matrix. So gradient of f1 x is the rows. So the f1 for the first row is 2x minus 1 1, and second one is this one, this minus e to the power minus x, and this one, right? So now we know how to find the matrix of f dash, right? Okay, now let's go to the next problem. So it says if f is a mapping from R2 to R is differentiable and d1f equals to d2f equals to 0. So all the partial derivatives here are 0. So then f is constant. Okay. So we proved this one. Actually this problem is true if from U to R, where U subset of R2 is an open connected set. So for any open connected set this holds, not just for R2, for any open connected set. Okay. So for the proof, so take 2 point. So this is step 1. Okay. So take these 2 points, A x1y and B x2y in U, such that, so y is fixed, so it lies in the same horizontal line, right? A x1y, this is B x2y, right? Such that the line segment joining this horizontal line joining these 2 points, joining A and B, lies in U, right? So we are taking 2 points in U such that the horizontal line joining these 2 points also lies in U, right? Okay. Now we define this single variable function gt is f t y, right? There is only one variable, which is t, right, on this interval x1 x2. Okay, so f is differentiable, so g is also differentiable, right? So g is differentiable, so g dash t, you can write g dash t. So g dash t is actually del f del x of ty, right? This is a partial derivative with respect to x, because y is fixed here in this line, right? So it is actually d1 of f ty, right? Partial derivative of with respect to x. Now by hypothesis we have d1 and d2f are always are zeros, so it is 0. So g dash t is 0 for all t in x1 to x2, right? Now we'll apply the mean value theorem on g. So by mean value theorem, what we have? We have gx2 minus gx1 is some g dash c into x2 minus x1, where c lies between this x1 and x2 in this interval, open interval x1 x2, right? This is the mean value theorem. Now g dash t is 0 in the whole interval x1 x2, so this is going to be 0 since g dash t is 0, right? So this implies gx2 equals to gx1. And what is gx2? Gx2 is f of x2y and gx1 is f of x1y, right? So f so this implies what? This x2y is actually b, so fb equals to fc. So we have proved that now that fa equals to fb. So the value in every horizontal line is same, right? Now similarly we can prove that the value in each vertical line is also equal, right? Similarly, by the same logic, we can prove that the same logic applies to any vertical segment using d2f equals to 0. Here we have used d1f is 0. So for vertical lines we can use d2f equals to 0. So this 2 implies f is constant along any horizontal or vertical line segment in U, right? The whole line has to be in U. So in first step we have proved that in each vertical or horizontal line f is constant, right? We have to prove that f is constant throughout U. Now in the first step we have proved it is constant in each horizontal and vertical line. Now in second step we'll show that so in second step we take P and Q 2 points, any 2 points in U that can be connected by a path made of a sequence of horizontal and vertical line. Segments in U. Right. Now we are taking P and Q be 2 points such that P and Q is in U. Right. Such that P and Q can be joined by vertical or horizontal line segments in U. Right. So since it is from P to Q, we are going by a sequence of horizontal and vertical line segments. So in these paths, F is constant. So FP will be FQ. So for any 2 points that can be joined by a sequence of horizontal or vertical line segments, F is constant there. Right? Now U was connected open set. So this means, so in step 3 we say that since U is open and connected, then any two point can be joined by this polygonal path. So this type of path actually called polygonal path of vertical and horizontal line segments. So any two points in U can be joined by polygonal path consisting of horizontal and vertical line segments, which entirely lying entirely within U. Right? So since U is open connected, any 2 points can be joined by this type of paths. So since any 2 points can be joined by these paths, so everywhere it is constant, right? For any 2 points, FP equals to FQ for any 2 points. So this means F is constant everywhere. So this implies F is constant. Right? So U is connected open connected, it is necessary. So there is a counter example, there is many counter example. If it is not open connected, we can find a mapping which is not constant. Right? So for counter example, so if the domain is like this and xy is here, these 2 points, then this line or this vertical line, this horizontal line is not does not lie entirely in U, right? So d1f, here we have used this d1f equals to 0 and d2f equals to 0. So we cannot use d1f to be 0 here, right? So for example, if we just choose, so just choose F to be disconnected. So let U be D1 union D2, right? Where D1 D2 are two disjoint Ds Suppose D1 is the ball centered at -3 0 with radius 1, and D2 is the ball centered at 3 0 centered at 1. Oh sorry, this is 1 also with radius 1, right? So -3 maybe here or like this 3 0, and we can define fxy to be 5 if xy belongs to D1 and 10 if xy belongs to D2, right? So D1 and D2f both are 0, but f is not constant, right? But f is not constant. So all the partial derivatives 0 means f is constant if this domain is open connected. Alright. Okay, so I will end here. If you have any doubt, you can ask now. Harshita? Okay, so if you don't have any doubts, I will end this session here. Okay. Okay. Thank you. Good night then.